Hello and welcome to the second lecture of our machine learning course. This time I will talk about linear regression. In this lecture, first I will talk about some data that we are going to use as an example to apply linear regression. Then I will talk about the main method that we need to understand now, which is the least mean squared method. And this method we are going to apply it using the stochastic gradient descent algorithm, or in general the gradient descent algorithm. So this is we are going to solve this using an iterative method. Then we will see how we can solve that simply using what we call some normal equations. And then I will explain probabilistic interpretation of this method. So why this is convenient to use this least mean square error for solving linear regression. And finally, I will explain a different method of linear regression, which is called locally weighted. The main idea behind this method is that we can fine-tune our model based on the point that we want to evaluate. So we can locally tune this model with respect to the point that we need to evaluate. Okay, so suppose that we have this data set. We have information about some houses. We have information about the living area of each of these houses and the price in, let's say, in thousands of dollars. So for example, we have a house of 560 feet square, and the price is 37,000 US dollars. So if we plot these points, we will see each of the houses as a point. So for example, this here represents a house that has a price, a living area slightly over 500 feet square, and a price slightly below $40,000. So we can plot the houses here as points. And the idea here in linear regression would be to find a curve, a function that passes very close to these points. So if we can estimate that line or that curve, then we can use it to predict the price of another house. For example, if we had a house of 1,500 feet square, we can simply evaluate that number in our function and then try to predict the price of that house. So let's call our first data here, the living area. Let's call this x1. This is going to be our input variable, and based on the input variable we will want to predict the output variable, which in this case is the price, and we are going to call this y. So as I said before, we have the points and we would like to find a line that passes very close to the points, and this line will have this expression. We can write that function as a straight line. This is the equation of a line. And you see here h of x, where h is going to be our model. This h comes from hypothesis. So in this case, we are making a hypothesis that our model could be a straight line. And this straight line has two parameters, theta 0 and theta 1. And is a function of our only variable available, which is x1. x1, remember, is the living area of the house. So the idea is that given the living area of a house, we can multiply it to some theta 1 and then some other parameter theta 0, and we will get our value in the y-axis here. This subindex theta here, it just says that our parameters in the model are thetas. Okay. Now, what happens if besides x1, besides the living area, we also have the number of bedrooms. So we can call this x2. This will be our second variable. And then we can add one more term to our model, and we will have then plus theta2 times x2. And as you can see, we can keep adding more and more input variables here, and this will give us more information to predict better, in this case, the price of the houses. Now, this expression here, if we add some x0 here, and we let this x0 to be 1 for every single house. So suppose that we have an extra column here that we are going to call it x0, and we will have 1 for every house. So we will have 1 here, 1, 1, 1 for every row in this table. So if we have this x0, we can rewrite this expression here in this way, like the sum from j equals 0 to n, where n will be in this case 2. So you will sum all the products theta j xj from j equals 0 to n. So this is a more compact way to represent our model. Now, if we use linear algebra notation and we store this theta 0, theta 1, and theta 2 in a vector, and we do the same with x0, x1, and x2, then we can rewrite all this expression as the dot product of the transpose of the vector theta and the vector x. So this is an even more compact way to represent our hypothesis. Okay, so let's remember how the polynomial functions looks like. So for example, suppose that you have the function y equals 1. This is equivalent to say y equals theta 0, which in this case is simply a straight line that is parallel to the x-axis. Okay. Now suppose that instead of having only one constant or one parameter, we multiply that parameter by the input variable x. Then in that case we will add some slope to our straight line. We can also, for example, have one constant that is independent of the input variable, and have another term that will multiply, or will consider the input variable times some parameter theta 1. In this case we have already defined a straight line that can have some slope, like in this case. So the result is that our previous function, I will go back, which was 2x, if we add something to this, for example, if we add some 1 to this, what we're doing is moving this line up 1 unit, which is what we are doing here. We are summing 1, and then the straight line will go up here in this case. If we keep adding terms, like for example, if we add some square term, like in this case 2 times x squared, then we are defining a parabola. And as you can see, as we keep adding terms to our polynomial, we make our polynomial more flexible. And this is important to understand, that sometimes you will need a lot of flexibility in your curves to be able to fit the points that you want to fit. Like in this case, we are talking about a parabola, And if we add another term, which in this case is a cubic term, then you allow the curve to turn not only towards one direction, like the previous one that we're turning up, but with a cubic term you allow the curve to turn down and also up. And you can keep adding more terms to give more flexibility to your curve. You can even play with the signs of the terms and then make the slope in the other direction. Okay, so the idea is that we need to find what is the best parameters theta that will make our hypothesis, our polynomial in this case, to pass very close to our points. One reasonable method to pick theta in such a way that our h is close to y, at least for our m training examples, will be using stochastic or gradient descent in general. So first we need to define a cost function or an error function. So it would allow us to, given some model, to measure how good or how bad this model is. So how close or how far away from the points this model passes by. So in this case we're going to call this cost error j. It is going to be a function of the theta, because depending on the theta our curve will take some shape. So there will be better thetas than others. And we are going to define this as 1/2 of the sum from I equals 1 to m. So we are going to sum for every example that we have, where m is the number of examples that we have. We are going to sum the square of this subtraction. This subtraction is a measure of how far away our model is from the points, from the real outputs of our points. So here we have xi representing some example I, and what is the output of this example I. So we could say maybe the size of the house of 500 feet square, for example, and the real price of the house, like let's say $100,000, for example. So this is going to be our cost function. We can initialize the parameters theta randomly, and then, as I said, to use the gradient descent algorithm to find the optimal thetas, the thetas that are going to minimize this. This is the cost function, which is, as I said, a measure of how close our model is passing by with respect of our set of points. Okay, so in gradient descent, what we do is that we have some parameters randomly generated initially, and then we apply many times an updated rule, and the rule is something like this. So we have, for a given theta j, we will give it the value that it has currently minus some alpha of the gradient of the cost function j with respect of theta j. So this alpha is a constant that takes values between 0 and 1. This is called the learning rate. So it is going to tell you how big or small are going to be the changes in the parameters. We will talk a bit more about this later. So now the important thing here is that we need to compute the gradient vector. So remember, given a function, the gradient is a vector that is pointing to the highest point in a surface. and what we want to do is to go in the opposite direction to that vector, and that is why we are going to subtract. If we were trying to maximize the function, this function here, we would have here a plus, because we want to make steps towards the highest point in our function that you can visualize as a surface. So what exactly is this algorithm going to do? So suppose that we have this cloud of points here, these red points, and when you say okay, let's assume that my polynomial is of degree 3, and you initialize the parameters. You give random values to these parameters, and you plot that polynomial. Maybe you will get a curve like this, for example, just a random curve. But as you go applying this rule to each of the parameters, since this is going to reduce the error of j, and j is a measurement of how far our model is to each of the points, you will see that this curve will start to turn and will adapt to the cloud of points. You will see that initially during the first steps, or during the first times that you apply the learning rule, the curve is going to turn a lot, but then the changes in the curve will be smaller and smaller every time. You will have time to experiment with this in the first exercise. Okay, so as you apply the learning rule, you will be finding the best parameters that minimize this function. And that means that if you have implemented correctly this algorithm, and if you plot the error of the model after each iteration, you will see that the error will start in some place up here, and then in the first steps this error will reduce very fast, and then will keep changing and going down and decreasing slowly up to some point that the error is not going down anymore. So this plot is very important in practical terms, because it's mainly the only way that we can use to determine if our model is adapting to our points. In the previous plot, in this one, it is easy to see if our model is adapting to the points, because these points are let's say in a 2-dimensional space, so we can plot it very easily. But usually in machine learning you work with points that are in dimension 10, dimension 20, dimension 100, or higher than that, and when you are using these points you cannot get these plots. You cannot see if your model is adapting. So the only feedback that you can get that your model is adapting is to plot the error of the model. Okay, so this is a very important plot that you need to make, and you will also need to do this for the first exercise, so you will have time to play with these curves. Okay, let's talk a bit more about the gradient descent. So this error that we are using, this j function, is a square function. So a square function means that it has a shape like this. It's like a parabola that is rotated, and that means that there is only one global minimum. When we apply the update rules of gradient descent, what we do is, like, first we initialize our parameters, so that is like locating your initial point in any part of the surface. Like, for example, suppose that you will start here, and then it's like letting go a small ball, and the ball is going to go of course, to the bottom of this surface. So this is the idea behind gradient descent, to compute in each point of the surface where you are located, where is the next step that you need to do in order to go down the surface. And as you can see here, the initial steps here are larger, and then they become smaller and smaller and smaller until the algorithm manages to find the global minimum of the surface. So let's see mathematically how we can compute the rule, because in this slide I said, okay, we need to update each of the parameters using some portion alpha of the partial derivative of the error with respect of theta j, but we cannot program this product now. We need to compute it numerically. So let's compute this, let's calculate the partial derivatives of the j, so we can have a rule that we can really program in our computer. So we need to compute then the partial derivative of j. I have written here j. I will do this with only one example. That's why you are not seeing here the sum for every point. We're going to compute considering that we have only one pair of points, but the application of this will be for every point. Okay, so we need to compute these partial derivatives. So we have these two here. When we compute the derivative, it moves down here as a product, and since we have 1/2 here, this 2 times 1/2 will become 1. And actually this is the reason why we have this 1/2 here. This is just a trick to simplify as much as possible the partial derivatives of the j function. That is the only reason actually why we have here since the beginning this 1/2. Okay, so this 2 comes here as a factor, then we keep here this subtraction, and then we need to compute the partial derivative of this with respect of theta j. And here first we write it that we need to compute that partial derivative. Then remember that this h of x could be written as the sum of the products theta and x for every possible term in our model. And in the next step we see that this can be simplified as this, because when we compute the derivative with respect of theta j, first of all we notice that this term here does not contain theta j, so it becomes 0. It's like computing the derivative of a number, a scalar. And here this is a sum of many terms, and only one term here will contain theta j. Okay, so for example, if we're computing this partial with respect of theta 2, only one term here will have theta 2, and that x that is beside theta 2 is going to be x2, which in this case is j. Okay, and then we can see that our initial version of the rule now can be written like this, and this is an update rule that we can really program. Okay, just consider or observe that here we have h minus y, and here in the rule we have now y minus h. The reason of that is that here, since it is gradient descent, we had this minus, but then when we write this here, we basically factorize this minus. It goes out. Minus times minus becomes plus, and then we simply write first the y, because it will become positive, and this will become negative when we factorize the minus. So the final rule is written like this. Now let me explain a bit how you need to apply this rule. So This is the rule. Now suppose that we have from our points that are going to be used for linear regression. Suppose that our third example is x3 equals 2, and the output for that is 20. y3 equals 20. And suppose also that your learning rate is 0.1. Consider also that you are using a polynomial of degree 3, so our hypothesis will have this form: theta 0 plus theta 1x plus theta 2x2 plus theta 3x3. And let's see how we can apply this learning rule. So suppose that you will update parameter 0, then you will have, the rule tells you that you should write theta 0 here, plus the alpha, our alpha in this example is 0.1, times the subtraction of the real output value for that example, in this case is 20, minus the evaluation of 2 in our polynomial. So this 2 is the xi, which in this case is 2, and we need to replace 2 here, here, and here. So here will be 2, here will be 2 to the power of 2, which is 4, here 2 to the power of 3, which will be 8, and we need to evaluate this with the current values of theta. Initially these values are just randomly generated, and this is going to give you a number. This number is going to be replaced here to compute the subtraction. And then we have this 2 to the power of 0, because here the rule, remember, is telling you you are going to put here the x or whatever it is beside the parameter j. So if we are updating theta 0, we need to put here the number that is here, which in this case is x to the power of 0, and x for this example is 2. So this is 2 to the power of 0, which is basically 1, and that is why here we don't write it, okay? But if you go to the other parameters, you can see clearly why this is 2 to the 0. So for example, to update theta 1, here we have theta 1. The last factor will be x to the power of 1, which is 2 to the power of 1, which is simply 2. When you update theta 2, you will multiply by x to the power of 2, which in this case 2 to the power of 2, which will be 4, and so on. Here we will have 2 to the power of 3. So remember, this is a general form. In this particular example, we are using a polynomial, but then we will see that you can also apply this to some other basis functions like Gaussian functions or sigmoidal functions. And then what you need to take into account that this last factor is simply the number that is multiplying the parameter that you are updating, which in this case is simply our input variable to some power, and the power is indicated by the index of the term, and the terms go from 0 to d, where d is the degree of the polynomial. Now we can implement this rule in several ways. One basic way to do that is just or is called a batch gradient descent, which is this way. It says repeat until convergence, so it means when the error is not going down anymore, we can stop. And we need to apply this for every j. J, remember, that is the index over the terms of the polynomial, starting from 0. So theta 0, theta 1, theta 2. And here you see that you need to compute first the sum of these products for every example, for every data point that you have. So first you need to compute this for every point. Suppose that you have 100 points. You need to compute these 100 products here. And the result, this sum, you will multiply it by alpha, and then you will update theta 0, and then theta 1, theta 2, and so on. So this implementation of the learning rule is called batch gradient descent. Okay, because here you need to compute the error with this set of points. There is a more practical way to implement this. This is called the stochastic gradient descent, and this is the version that you are going to implement in the exercise 1. So it looks very similar, but there's an important difference, and the important difference is that we don't have this sum here in the rule. So if you notice here, we don't have the sum, and this sum changes to a for loop. So we have here 2 loops. The outer loop, it just tells you, okay, you have to repeat this until the error is smaller, as smaller as possible. And then you have this second iteration here, this inner iteration that will go from I equals 1 to m, where I is the index over the points that you are going to use. Okay, so you will take the first example and update every parameter of your model. So if your model has 4 parameters, you will update the 4 parameters using the first example. Once you have updated using the first example, you will move to the second example and update again the 4 parameters of your model. Then you move to the third example and do the same. So this loop here will move from one example to the other. So as you can see, this will start making changes to the parameters much faster than this method here, because imagine that you have instead of having 100 examples, imagine that you have 1 million examples. Just to apply this update rule for one parameter, let's say theta 0, you will need to compute these products here for 1 million points. Okay, and after that, then you can update theta 0 one time. In this case, you say, no, 1 million is a lot, I don't want to wait that much. I will take my first example, compute the error, and update my parameter theta 0, then theta 1, 2, and 3. Then I will move to the second example and update again the parameters. So even though it looks very similar, the advantage of the stochastic gradient descent is that you can see much faster how the curve is adapting to the point, so how the error is going down. Now, nowadays there is let's say a more practical way to apply this stochastic gradient descent. It is called mini batch gradient descent. So instead of updating the parameters considering only one example, we take mini batches of examples. So for example, you say, I'm going to update it using 10 examples. So you compute these products for 10 examples and then update your parameters. Then you take another 10 examples, compute the products, sum the results, and update the parameters. Okay, and in practical terms, this k usually goes from 10 to 1000. So it will depend on how much data you have and how much computational power you have. So this is by far like the most common way to train models nowadays.